appreciate the opportunity to come and share a little bit with you. I've known Scott for a long time and I appreciate meeting Don, and hopefully we can share a little bit about some of the aspects of materials joining, particularly dissimilar materials. I do not represent myself as an expert, but one of many experts we have within our organization. So I will not give a commercial, but it would probably be important to tell you who EWI is. We are an engineering and technology services organization dedicated to helping manufacturers around the world really introduce and develop new products and new manufacturing processes. We specialize in overcoming what we call the valley of death, from very basic preliminary research to making technology suitable for commercial deployment. So as you develop new ideas for products, we really help companies and people like you get through that process and really make them suitable for commercial manufacturing. We are an organization that was founded partly by Ohio State University back in 1984. We appreciate that. We're actually on the West Campus, and we also lease space back to Ohio State University's Material Science and Engineering Department. So we have a great collaborative relationship with the university. We appreciate it. So my objectives today is really to introduce the topic of dissimilar materials joining. I'll present just an overview. There's a lot of detail here, a lot of slides. I'm going to go fairly quickly and encourage you to pick up one of my business cards or see me afterwards if you have specific questions. I can connect you with one of our techno resources. One of the reasons we think about dissimilar materials, particularly looking at metals today, there are many reasons to use dissimilar materials. Everything from lightweighting to taking advantage of joining of two different materials to conserve a valuable alloy that may be very expensive to use, preventing corrosion, and getting even tailored properties. There's many ways to do that, and we play in many different market sectors. Not everything we make is as big as an airplane or a ship. We do get involved with a lot of electronic devices and medical devices as well, where these same technologies are very valuable. In terms of medical applications, I'm not going to spend a lot of time talking about them, but they are applied very frequently in orthopedic devices, surgical devices. I saw an example actually just a few weeks ago of a knee implant where a cobalt chrome material had been plated basically or coated with a tantalum surface, both to prevent wear, give you increased abrasion resistance, as well as increase the ossification and bone ingrowth of the implant. So that's an example of dissimilar materials joining. We also work quite a bit on electronic implantable devices. So we deal a lot of titaniums and interconnecting devices that provide electrical connection to those as well. So there are many issues to consider, both from a metallurgical perspective, physical perspective, when you're thinking about joining materials that are, in fact, don't naturally want to go together. It includes everything from how you design the joint, what the material thicknesses are. Often there's a difference in coefficient of thermal expansion between two materials that makes it very difficult to put them together. Sometimes the melting temperatures are very important to consider, as well as the brittleness. In particular, we're going to talk a little bit today about several processes that lend themselves to joining of dissimilar materials. I'm going to give you a few examples, and not necessarily a lot of depth, but the most common approach really is what we call a solid state process. And I'll explain those three processes shown there and why that's important, why it's an important approach. We'll talk a little about soldering and brazing, fairly old technology in a sense, but we've pretty much perfected and developed a lot in what we call ultrasonic soldering, ultrasonic brazing, which is a pretty unique way to join materials. Talk a little bit about laser welding, and then just a little bit about adhesives as well. So the first one, really a solid state welding process. There are a couple of ways to join metals. One is a fusion process. And if you think about welding, which is one of our basic core technologies, you're talking about typically about arc welding. You strike an arc, provide electrical energy or some sort of energy, two metals melt, they flow together, you push them together, they solidify, and you have a joint. Well, if you have two identical metals, that works extremely well. If in the case of dissimilar metals, you basically cause those materials to melt, and what forms in the middle usually forms the third independent alloy of those two base metals. And very typically that new alloy is called an intermetallic, and very typically it has very undesirable properties, including the fact it's typically brittle. So now you formed a joint that is much, much weaker than the base materials. And that's very frequent. One of the most common things we hear now, particularly in the automotive industry, where there's a lot of interest in lightweighting, trying to join aluminum to steel. You can have some aluminum structure, some steel. How do you put those together? Well, you can't arc weld them. You can't laser weld them because you form these brittle intermetallics that absolutely will fail. So the alternative approach is a solid state welding process. In this case, you don't really melt the two materials. And one of our chief scientists is a Dr. Jerry Gould, who got his PhD from Carnegie Mellon, very strong metallurgist. And he tells the story that if you actually get two metals together, most common metals, and get them perfectly flat and remove all the surface contaminants, all the oxides, the materials will stick together and bond very well. That's a solid state bond. So nearly all the processes we talk about in terms of solid state welding rely upon those basic principles. Make them perfectly flat, remove all the contaminants, boom, you've got a bond. So there are ways to do that. And there's several listed here. There's flash butt welding, which is more of a forging process. It's used pretty rarely now, but there's a resistance projection welding I'll talk about a little bit more. A mash seam welding, which is a kind of a continuous process where actually mash, part forging and part heating up the materials through electrical resistance. Linear friction welding and things like that. So here's an example. I mentioned aluminum to steel. May not be common in medical applications, just to show you what we're talking about. We have a couple of big machines over in our lab that's used to make cylindrical or actually symmetric products. In this case, you would spin one of the materials up at very high speeds, either with a flywheel or a direct drive. The other is stationary, and then you push them together. And as you do that, it creates quite a bit of frictional heat. The materials soften, and in the process, that friction and the heat removes all the surface contaminants, makes the surfaces perfectly flat. And over here, you'll see, that's what the bond looks like. Two materials, there's no joining of the materials in a separate alloy, and it makes a very, very strong bond. So that's what we're talking about in terms of inertial welding. There's another process called resistance projection welding. It's very, very commonly used. In this case, we're actually using a projection, shown by this little pinhead, if you will, that actually concentrates the electrical energy and resistance heating, so then you can form, and the projection also increases the scrubbing of the contaminants, forms a very nice weld very, very quickly. This particular application is a 5,000 stick nickel pin, it's a titanium case with a nickel pin welded to it. It happens to be a medical device, an energy storage device. You may even figure out what that means. But in this case, we could not get underneath to support it, so the projection was also important in making that weld. But it tells you some examples of some things we can do. Okay, move on. So there's another process which is very, very common. This is called ultrasonic metal welding. Very similar in a lot of regards. In this case, the energy is applied horizontally, or you have a shaft providing a static force, you see on the far right. Get my pointer to work. And then you translate, you provide ultrasonic energy that actually moves the parts you want to join horizontally back and forth. You're doing a scrubbing action. Typically, it's at 20 hertz of a rate, 20,000 cycles per second. It could be 40, even higher. You apply a force, but as you rub them together, you see what's happening here. All the surface asperities and the contaminants are ground up, so basically smooth. Now, these surface contaminants typically are embedded, but you still have enough bonding to form a great bond. So this is particularly useful when you're forming materials that don't want to go together. In this case, it's aluminum, copper, nickel. Very common in a lot of battery applications, any kind of power applications as well. And you see a couple examples here on the right. Very, very common and very fast as well. And low power, fairly low cost. I have some samples here too. The next one is really brazing and soldering. Brazing and soldering is when you get to use a third material, intermediate material that is more amenable to bonding with each of the other materials in and of itself. So typically you would have to, again, remove the surface oxides to put a braze or solder down. If you've ever soldered water pipes in your home, you know you use a flux. The flux is an acid typically, removes the oxide and makes that surface pure, so then the solder sticks to that. You apply the solder or braze to the other material, then reflow them, heat them up, they flow together. The challenge there is the joint is only as strong as that intermediate material. The solders typically are lower strength materials, but they melt at lower temperatures, roughly below 450 degrees F. The brazes are higher than that. But the interesting thing is you can use these to join a variety of different materials, including metals to ceramics, called active brazing. You can braze carbon fiber fabrics and carbides, nitrides, and a lot of things like that. And I have one example. I'm only going to point it out, then I'll put it over here so you can take a look. This is a little tricky. It's a little honeycomb structure. You can't see it this far away. But we've managed to use resistance welding, like we talked about earlier, to join titanium to an inconel, which is a nickel alloy, very strong, very thin sheet. Then we've used a braze material to braze the nickel or inconel to a inconel plate. I'll try to set around as well. So a subset of this is what we call ultrasonic soldering. This is one of my pet technologies, EWI. We didn't invent it, but we have perfected it and really expanded upon it greatly. In this case, what we're using is ultrasonic energy combined with a soldering iron. So if you look carefully at the diagram here, we have a soldering iron, if you will, that heats up a solder pool, and once it's molten solder on some sort of base material you're trying to join, then you turn on the ultrasonic. So ultrasonic is vibration, again, in the axial direction at a rate typically of 20,000 cycles per second. So it's very fast, very low amplitudes in the order of 5 or 10 microns, peak to peak. But as that happens, it creates cavitation bubbles. And those bubbles, cavitation bubbles, are very energetic. They immediately collapse. And that collapsing is very dynamic. It essentially scrubs the oxides and any contaminants off the surface. And as you make that surface clean, guess what happens? The solder flows right behind it. So this is a completely fluxless process. You don't have to use any acids or worry about where, clean up and take care of that, which is a big environmental issue. The beauty of this is you can use this process to basically lay solder or a braze down on some material, do the same thing on some other very different material, flow them together, and you're able to form a bond. That's what this is all about. And the reason I think it's pretty cool, the things you can do with it. So I have an example here too, another one of my favorites. This, you can take it out of the case if you want. We've actually soldered a penny to a piece of glass. Solder, believe it or not, yeah. So don't drop it or break it. Well, we could make some more, but I'd be in trouble if I didn't return it. This is a more interesting one because now we've actually soldered with this process alumina, which is a ceramic, to titanium. The ceramic and titanium solder together. On the other side, we have aluminum soldered to titanium and aluminum soldered to alumina, the ceramic. So 3 different combinations here, all with this process. And so the neat thing about it is you can now join metals to a wide variety of glasses and ceramics. Here's a silicon carbide to a titanium down here on the far right. We have titanium, 6-4 to glass, glass to ceramic seals, all kinds of things, which is, you know, for a lot of medical devices, there are a lot of ceramics and glasses used. In implantables, there's a feed-through. Typically, this uses the glass melting technology. This is an alternative approach. Obviously, we talked a little bit about orthopedic implants. A lot of ceramics used, again, a lot of very sophisticated metals. This is a very cool approach to do that as well. The last example I have is actually a woven fabric with a metal fiber woven in. I believe it's titanium. You can see this. We've actually soldered an alumina or ceramic plate to it. And it's a great bond as well. So little things like that are interesting. And that's one of the things that people call us the most for is putting things together that naturally don't want to go together. We can also talk a bit about laser welding. And as I mentioned early on, laser welding is a fusion process. And normally it's not good for dissimilar materials, metals. But the fairly recent new developments in lasers are what we call fiber lasers. And the lasing process is actually accomplished in a fiber optic cable and delivered through a fiber optic cable. In this case, is a very, very focused laser beam. Typically, you can focus it in the 10 micron range. It has very high energy density. So you can do things on a very, very small scale that will allow you to weld dissimilar materials because you can now very carefully control the heat input because the focus size is so small. And also you can weld very fast. So it's not always the best, but it will allow you to do some things in a fusion process that you could not do otherwise. And particularly the fact that you can now manipulate the beam very quickly and make those welds, it lends itself well to high production volumes that some of our clients face as well. There are some disadvantages. The laser costs compared to other processes is still relatively high. The cost is coming down, the efficiencies are going up, so it's getting better. It does require a very good fit up. You can't fill a gap. Have to have the materials touching perfectly. So, but it is another option. And here just shows an example. Here we have an XY table where we go very fast, up to 2 meters per second. And over on the far right, we actually have a patented technology of using lasers to join nitinol to stainless steel. And that particular example is a guide wire. You're probably familiar with that technology. We also applied it to hypo tubes, things like that, very thin thicknesses. So one of the specialties we have. And I have to apologize for this slide because it's kind of a mixed message. I meant to talk about adhesives, but actually showing some pictures of joining of plastics that are not dissimilar. They're all dissimilar materials. So ignore the photos for a minute. We have quite a bit of expertise in adhesives, although we do not formulate adhesives. There are thousands of adhesives made by many great manufacturers. We specialize in designing adhesive systems, particularly focused on surface preparation, delivery, curing, those kind of things. And particularly as it pertains to dissimilar materials, we've applied adhesives to join metals to plastics, elastomers. Use Dr. Guan's example, exactly what that is. Composites to metals, composites to wood, things like that. A lot of things you think are not possible can be done with adhesives nowadays. And then my last slide really talks about kind of unique technology that we invented called weld bonding. In this case, we've actually combined the benefits of adhesive bonding with welding. The welding could be a resistive spot weld process, it could be a laser weld, and we take advantage of the exceptional shear strength supplied by the adhesive and the peel strength provided by the lasers. And one example was a lightweight aircraft structure. We use this process, also very economical to build. And it doesn't apply necessarily to all dissimilar materials, but it's one more option, and I thought I would include that as well. So I think that's it. It's, again, a very fast, high-level overview, a variety of methodologies and technologies for dissimilar materials. We work in a wide range of sizes, shapes, materials, and applications, and we'd be happy to help you in any medical if you get the opportunity. Thank you.